Welcome students to the next video in discrete math series. I am uploading videos on discrete maths and other topics as well. So if you are new to the channel, please subscribe it so that you can watch the videos as per your requirement. Right. So let's start directly. So first thing that we are going to talk about in this is relation. And we will also talk about what are different kind of relation like symmetric, transitive, antisymmetric, reflexive, and we will see different examples to understand the things better. But before I discuss the topic of relation, I just want to define there is something called Cartesian product. So to define the Cartesian product is defined between two sets A and B. Right. So suppose I have the first set A which contains two elements, 1 A and B, and the second set contains three elements, 1, 2 and 3. So what is A cross B, or what is the Cartesian product between A and B? So it will be A comma 1. So here in the ordered pair, and this is ordered pair means A comma 1 is not equal to 1 comma A. When I say ordered pair means A comma 1 is not equal to 1 comma A. They are two different things because the order is important here. So the first element will be coming from the first set and the second element will come from the second set. So I will have A comma 1. I will also have A comma 2 and A comma 3. And we will have B comma 1. We will have B comma 2 and B comma 3. So in total in A cross B we have how many elements? We have 6 elements, right? So this is a general idea that if the number of elements which we represent by this, the number of elements in A is equal to M and the number of elements in B is equal to N, then the number of elements in A cross B is equal to M into N. And when I am talking about the element of A cross B, the ordered pair are its elements. Like A comma 1, this ordered pair is one element, A comma 2 is the second element, A comma 3 is the third element, and so on. So there are 6 elements. Now when we are talking about relation between A and B, it is the subset of, so look at the definition, let A and B be sets, then relation from A to B is defined as subset of A cross B. And how do we denote? We denote that A comma B belongs to R, and we also write it A is related to B. Right. So this is how you define the relation between two sets. We can also define the relation on a set. So when I talk about relation on a set, we can define the relation on a set A by defining it as the subset of the Cartesian product between A and A, right? So if I ask you what is the Cartesian product of A and A, so here the first element will be A comma A, second element will be A comma B, then we will have element like B comma A, and we will have element like B comma B. If I take the Cartesian product between the set A and the set A, so in this case how many elements are there? 4 elements are there. So it means that if the number of elements in A is equal to n, then the number of elements in the Cartesian product between A and A will be equal to n into n, that is equal to n square, right? Now to understand it better, 2-3 points I want to highlight. The first point I want to highlight that when we are defining the relation on a set, and our focus will be more on the relation on a set. So suppose I am taking a set A with n number of elements, then the number of elements in A cross A we have just seen is equal to n square. And in our set theory class, in earlier classes, we have seen that if a set has suppose m element, a set with m elements will have 2 to the power m subsets. I hope you remember. I think the term that we have seen earlier is also known as power set. So power set contains all the subsets of a particular set, and total number of subsets are 2 to the power m. So if I am defining the relation on a set with n elements, as you have already seen the definition, that what will be the relation on a set A? It will be the subset of A cross A. Now A cross A has how many elements? N square elements. So the total number of relation, and this is important, you need to remember this. So total number of relations defined or possible defined on a set with n elements. How many total number of relations will be there? It will be 2 to the power n square. Why 2 to the power n square? Because total number of elements in A cross A is n square, and the relation on a set A is the number of subsets that is possible of A cross A. To understand it better, suppose I take a simple example. Suppose I take a set which contains just 3 elements, 1, 2, 3. And if I ask you what is A cross A, so you will say that it has 9 elements, 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. Now let us write some relation that we can define on it. So suppose I am writing the first relation R1, which is empty set. It is also a relation because empty set is also a subset of A cross A. Suppose I write another relation R2. So I can take elements like 1, 1. This contains just one element. So 1, 1 is also a relation. Suppose I define another relation where I take 1, 1, 2, 3 and 3, 1. So this is also an example of a relation on the set A. I can take another relation. Suppose I take, let me call it R3, and let me write R4 here, where I include 1, 1, 1, 2, 2, 2, and 3, 3. Right. So all these examples that I am writing are relation, because how many elements are there in A? In elements, number of elements in A are 3. So number of elements in A cross A is 3 into 3, that is equal to 9. And how many relations are possible? 2 to the power 9 number of relations are possible. So in total 2 to the power 9, you can calculate how much it will be. So on a set, I repeat this thing, that if the set has n number of elements, its Cartesian product will have n square number of elements, and total number of relation possible will be 2 to the power n square. I hope it is clear up to this. So see, here we have a question that how many relations are there on a set with n elements. So for that, I already have answered you that number of elements in A is equal to n. Number of elements in A cross A is equal to n square. So the number of relations, how many relations are there? 2 to the power n square. Keep this in mind. Now I want to take one or two quick example so that you understand the relation thing better. And relations can also be represented using the different properties of it. So suppose I take a set which contains 4 elements like 1, 2, 3 and 4. And on this I am defining a relation, let me call it R1. So what is the relation R1? That it contains all those ordered pair which looks like A, B, and the property that it follows, that it follows the property that A divides B. Now this is a kind of approach through which we can represent the relation, but I want you to understand that if I am taking all those ordered pair A, B, where A divides B, then what are the elements there in the relation R1? So on this set, it is very clear that 1 divide 1, right? So 1, 1 will be there. 1 also divides 2, so 1, 2 will also be there. 1, 3 will also be there, and 1, 4 will also be there, because 1 divides every number, so it is all possible there. Now if I take 2, 2 divides 2 and 2 divides 4, so these two elements will be there. 2 does not divide 3, so 2 comma 3 will not be there. If I take 3, then 3 divides 3, because 3 divides just one element of this set, so 3 comma 3 will be there, and finally 4 comma 4 will be there. So what is the relation R1? Relation R1 is the relation which contains these elements, right? Suppose I ask you to define a relation like R2, where R2 can be defined as, what is the property that R2 follows? That it has all the ordered pair like A comma B, where A plus B is equal to 4. And I ask you write all the relations, all the elements in R2, means R2 is the relation, and write all the elements in R2. So what are those elements? I am going to suppose I take 1, so 1 comma 3 will be equal to 4, so 1 comma 3 will be there. If I take 2, then 2 comma 2 should be there, because 2 plus 2 will be 4. And if I take 3, then 3 comma 1 should be there, because 3 plus 1 is also equal to 4. And here you note that I don't have the any other possibility. Like if I take 4, then I can't take any other element, because 4 comma anything will be, or 4 plus anything will be more than 4. We want only those ordered pair which satisfies this characteristic that A plus B should be equal to 4. So I guess you are clear about few things. One is what is the Cartesian product, how to define the relation on a set, how many total number of relations are possible on a set, and given any specific characteristic of the relation, we will be able to write the types of it, like the elements can be listed. Like here A divides B, so I have listed all the elements which satisfy this property that A divides B. And similarly here also I have listed all the properties, all the elements which satisfies the property that A plus B is equal to 4. Now let us move and look at the definition of the different kinds of relation. So the first one is a reflexive relation. So a relation on a set A is called reflexive if it contains all the elements of type A comma A, and that should be true for every element of the set A, right? I will explain through example also. So first let me define all of it. What is symmetric relation? A relation on a set A is called symmetric if B comma A belongs to R whenever A comma B is in R, and that should be true for every element, all elements A comma B in the set A, right? So whenever we have A comma B, then B comma A should also be there. That is the definition of the symmetric relation. What is antisymmetric or antisymmetric relation? So a relation on a set A is called antisymmetric if whenever A comma B is in R, then B comma A should not be in R unless A and B are equal, right? So it means that A comma B, if belongs to R, then B comma A should not be in R except in those cases when A and B are equal. Or this can also be seen as the definition can also be seen as that if A comma B belongs to R and B comma A also belongs to R, so in that case A and B must be equal. Okay, and finally let us define the transitive relation. So how do you define the transitive relation? A relation R on a set A is called transitive if whenever A comma B is in R and B comma C is in R, then A comma C should be in R, right? And this is true, this should be true for all ABC in the set A. It means what? That it is kind of transitive relation, that A is related to B, and if B is related to C, then A should be related to C. Okay, so reflexive, symmetric, antisymmetric and transitive, these four relations or kind of relations we have defined. Now let us look at the examples related to each of this, and we are going to take a lot of examples, and I would suggest you to take a pen and paper so that you can also do together with me, right? So let's move. So here we have a list of problems, and through these problems we are going to learn that how to decide that whether the given relations are reflexive, symmetric, antisymmetric or transitive. So a set is given and the set contains the four elements like 1, 2, 3 and 4, and the relations are defined like this. Now first of all, let us talk about which of the relations are reflexive. So what was the definition? I hope I would suggest you to note down the definition so that you get the point. So the definition of reflexive relation was that it should contain all elements of type AA. All elements of type AA should be in R for every element A in capital A, right, in the set A. So if I look at R1, it has 1 1, it has 2 2, it has 4 4, but this does not have 3 3. So R1 is not reflexive. So if I take R1, R1 is not reflexive, right? Now what about R2? So R2 has 1 1, but it neither has 2 2, 3 3 or 4 4. So R2 is also not reflexive. If I talk about R3, R3 has 1 1, R3 has 2 2, R3 has 3 3 and R3 also has 4 4, right? So R3 is going to have R3 is going to be a reflexive relation. Okay. Let us look at R4. So in R4, 1 1 is not there, or neither 2 2, 3 3 or 4 4. See, one thing that I hope you are clear, that when I am talking about the reflexive relation, all ordered pair of AA types should be there. Means like here in R3, 1 1 was present, 2 2 is also there, 3 3 is present and 4 4 is also present. If any of this combination is missing, that will not be reflexive. So clearly R4 is not reflexive. What about R5? 1 1 present, 2 2 present, 3 3 present, 4 4 present. So R5 is also reflexive, and clearly R6 is not reflexive because none of the type 1 1 2 2 3 3 or 4 4 are present there. So in this case only two relations, that is R3 and R5, are reflexive relation. I hope you have understood. If you have not, please take a pause and look at the definition again. Now how many of them are symmetric relations? So we are going to talk about them one by one. So if I talk about R1, R1 has 1 comma 2, but R1 also has 2 comma 1. What is the definition of a symmetric relation? That if AB belongs to R, then BA should also belong to R. BA should also belong to R. So if I look at 1 1, 1 1 is also there, means for 1 1 or AA type it will be like not a confusion. But 1 2 is there and 2 1 is there, so that okay. But if you look at this element 3 comma 4, 3 comma 4 is present but 4 comma 3 is not present. 3 comma 4 is present but 4 comma 3 is not present. So R1 will not be a symmetric relation. What about R2? So in R2 we have 1 comma 1, fine, and 1 comma 1 and 2 comma 1 both are present. So whenever we have something like A comma B, then B comma A should also be there. So here we have 1 comma 2 and we also have 2 comma 1. So this R2 is a symmetric relation. What about R3? So in R3 we have 1 comma 2, then 2 comma 1 should be present. Okay, we have 1 comma 4, so 4 comma 1 should be present. We have 2 comma 1 and 1 comma 2, that we already have checked. 2 comma 2 is also there, 3 comma 3 is also there. 4 comma 1 is there, 1 comma 4 is there. So R3 is also symmetric. I hope you are getting the definition. AB is there, then BA should be there. If AB is not there, then BA there or not there does not matter. If AB is there, then BA should be there, means both AB and BA type of elements should be there. So here R2 and R3 are symmetric. What about R4? So 2 1 is there but 1 2 is not there. So R4 is not symmetric. See, when once we get one such pair for which A, B and BA both are not there, then we don't check about others. So clearly here 2 comma 1 is there, but 1 comma 2 is not there. So I don't check about others, it is not symmetric. What about R5? So in R5 1 comma 2 is there, but do we have 2 comma 1? No, here 1 comma 2, 2 comma 1, no, we don't have 2 comma 1. So R5 is also not symmetric, and clearly R6 is not symmetric because 3 comma 4 is there, but 4 comma 3 is not there. So R6 is also not symmetric, right? So only two of them are symmetric, that is R2 and R3. What about antisymmetric or antisymmetric? So what was the definition? That antisymmetric relations are those relations in which if A comma B is there, then B comma A should not be there. I repeat, if A comma B is there, if A comma B is in R, then B comma A should not be in R except when A and B are equal. If A and B are equal, then it may be present. So now look at the relations one by one. What about R1? So R1 is like antisymmetric or not? So here 1 comma 2 is there and 2 comma 1 is also there. So both 1 comma 2 and 2 comma 1 are there. So antisymmetric? No, R1 is not antisymmetric. R2 is also not antisymmetric because both 1 comma 2 and 2 comma 1 are there, even though 1 and 2 are not equal. I hope you are getting the definition. If 1 comma 2 is present, then 2 comma 1 should not be present, except when 1 and 2 are equal, but 1 and 2 are certainly not equal, so it is also not antisymmetric. What about R3? So in R3 we have 1 comma 2 and we also have 2 comma 1. See, 1 comma 2 and 2 comma 1 both are there, so R3 is also not antisymmetric. What about R4? So in R4 2 comma 1 is there, 1 comma 2 is not there, good. 3 comma 1, 1 comma 3 is not there. 3 comma 2, 2 comma 3 is not there. 4 comma 1, 1 comma 4 is not there. 4 comma 2, 2 comma 4 is not there. 4 comma 3, 3 comma 4 is not there. So R4 is antisymmetric. So we got our first antisymmetric relation. What about R5? 1 1. So if 1 and 1 are equal, then it may be present. 1 2 is there, no 2 1 is present. 1 3 is there, no 3 1 is present. 1 4 is there, 4 1 is not present. 2 comma 2 may be present because 2 and 2 are equal. 2 comma 3 is there, 3 comma 2 not present. 2 comma 4 is there, 4 comma 2 not present. 3 comma 3 can be present because 3 and 3 are equal. 3 comma 4 is there, 4 comma 3 is not there, and 4 comma 4 may be present because 4 and 4 are equal. So here R5 is also antisymmetric. And what about R6? R6 has just one element, 3 comma 4. So 4 comma 3 is not present. So R6 is also antisymmetric. So the last three, R4, R5 and R6 are antisymmetric relation. Finally, we also want to check about transitive relation, and since I am going to write here for transitive relation, right, transitive. So ladies and gentlemen, which of the relations are transitive? And checking transitive is slightly more involved, so you need to be very careful. So if I look at this one, R1, whether R1 is transitive. So if you look at R1, you note here that you have a point 3 comma 4 here, and you have a point 4 comma 4 and 4 comma 1, rather they are very close to each other. You have a point 3 comma 4 and you have another point 4 comma 1, means the 3 comma 4 point is there and 4 comma 1 point is also there, but 3 comma 1 is not there. 3 comma 1 is not present, because for it to be transitive, if 3 comma 4 is there and 4 comma 1 is there, then 3 goes to 4, 4 goes to 1. So 3 should go to 1, means 3 comma 1 should be there, but 3 comma 1 is not there. So that is why the relation R1 is not transitive. What about R2? So R2 is clearly not transitive, because if I take in R2 2 comma 1, 2 comma 1 is present in R2 and 1 comma 2 is also present in R2. So 2 goes to 1, 1 goes to 2. So 2 should go to 2. So 2 comma 2 should be present in R2, but 2 comma 2 is not present in R2. So R2 is also not symmetric. What about R3? So in R3 we note that we have a number 4 comma 1, right? So we have an ordered pair 4 comma 1, and we have an ordered pair 1 comma 2. So 4 comma 1 is there, 1 comma 2 is there. So let me write it: 4 comma 1 is there, and 1 comma 2 is there. Sorry, 4 comma 1 is there and 1 comma 2 is there. So which element should be there? 4 comma 2 element should be there. But in R3, do we have 4 comma 2? No, we don't have 4 comma 2. So R3 is also not transitive. I hope you are getting it. I repeat this R3 example again. In R3 we have 4 comma 1. Look at this element 4 comma 1, and look at the element 1 comma 2. So 4 going to 1 and 1 is going to 2, but 4 is not going to 2. So that is why this is not transitive. What about R4? R4 you can verify is transitive, right? So why it is transitive? Because you take any two pair, like if you take 2 comma 1, then there is no element which takes 1 to the next element. So there is no problem here. 3 comma 1, then there is nothing like 1 comma something. Here it is 3 comma 2, there is nothing like 2 comma something. Here it is 4 comma 1, again there is nothing like 1 comma something. 4 comma 2, and there is nothing, 4 comma 2 is there and 2 comma 1 is there. So 4 comma 1 should be there. So you see 4 comma 2 is there and 2 comma 1 is there. So in that case, what we should have? We should have 4 comma 1, which is present. And 4 comma 3 is there, 4 comma 3 is there, and 3 comma 2 is there. So 4 comma 2 should also be there, which is present here, 4 comma 2. So R4 is transitive. Similarly, you can verify that R5 and R6 are also transitive. Clearly R6 is transitive because 3 comma 4 is there, but there is no element which is like 4 comma something. Like, so when we don't have 3 comma 4 or 4 comma something, then we don't talk about what is where 3 will go. 3 is going to 4, but 4 is not being taken to some other element. So that of course is a transitive element. Some students do have this confusion that if 3 comma 4 is there, and see, let me explain it through this way. Like if I say that 3 comma 4 is present and 4 comma some element, this element may be anything. Suppose I say alpha. So 3 comma 4 is there and 4 comma alpha is there. But if 3 comma alpha is not there, then we say it is not transitive. But 3 comma 4 is present and 4 comma alpha type element is not present, then we don't care that whether 3 goes to which element, right? So this R6 is also transitive. I leave this for you to verify that R5 is also transitive. Why R5 is transitive? Because here you will not be able to find any two such pair where A goes to B and B goes to C, but A does not go to C. We are saying that when we say it is not transitive, when A goes to B and B goes to C, then A should go to C. If A does not go to C, then it will be not transitive. So whenever we have something like AB and BC, then AC must be there. That is the requirement of the relation to be transitive, right? Let us see one more example. Let's take another example. So here we are going to define the relation on the set of integers, which is an infinite set, right? The previous example that I discussed, that was containing only 4 elements, 1, 2, 3, 4. Here the set of integers contain infinitely many elements. So let us look at them, that which of them are reflexive, symmetric, transitive and antisymmetric. So first, reflexive. And here we need to be slightly more abstract in our approach. So here R1 is defined as A comma B, where A is less than or equal to B. So certainly this set R1 or this relation R1 will contain all elements of type AA. All elements of type AA will belong to R1. Why? Because A is certainly less than or equal to A. Right? A should be less than or equal to A. So for all element A belonging to the set of integer Z, A comma A will belong to R1. So that is why R1 is reflexive. What about R2? So here it is containing elements like A comma B. So if I write where A is greater than B, so here A comma A will not belong to R1 for any except I think for no element A is not going to be greater than any of the element, right? So any of the element like A is certainly not greater than A for any Z. That is what I am saying, that if I write A is greater than A, so this is not true for any of the element that belongs to this. So this R2 is not reflexive, right? What about R3? So R3 is that it will have all the elements A comma B where A is equal to B or A is equal to minus B. So certainly it is reflexive. Why it is reflexive? Because it will contain, if I take any element A, suppose I take element like 7. So 7 comma 7 will be there because 7 is equal to 7. So all the elements A comma A type will be there. So R3 is also reflexive. R4 of course is reflexive because it contains only those elements for which A comma B is there, means it will have 0 comma 0, 1 comma 1, minus 1 comma minus 1. So this is of course reflexive, no doubt about this. What about this? Is it reflexive? So if I take any element A comma B for which A is equal to B plus 1, so certainly it is not reflexive because if I take for example 1 comma 1, so 1 comma 1 will not be in R5. Why it will not be in R5? Because certainly 1 is not equal to 1 plus 1, right? If I take 2 comma 2, so 2 comma 2 is also not in R5. Why? Because 2 is certainly not equal to 2 plus 1. Any element can't be equal to that element plus 1. So certainly it is not reflexive, right? And what about R6? So R6, like it is saying that it will have only those elements for which A comma B is less than or equal to 3. So certainly it will not have elements like 2 comma 2, because if I take element 2 comma 2, then 2 plus 2 is 4, which is not less than or equal to 3. So this is also not reflexive. So the reflexive relations in this case was, what was the reflexive relation? R1 was reflexive, R3 was reflexive, and R4 was reflexive, right? Now let us talk about symmetric type. Symmetric. So A comma B is less than or equal to B, right? So it is not symmetric because it is saying that it should have elements where A is less than or equal to B, right? So for example, if I take the element like 1 comma 2, then 1 comma 2 will be in R2 because in R1. I am talking about R1. So 1 comma 2 is in R1 because 1 is less than or equal to 2, but 2 comma 1 is not in R1. It is not in R1. Why? Because 2 is not less than or equal to 1. So that is why it is not symmetric. R1 is not symmetric. I am writing here. What about R2? So R2 is certainly not symmetric because if A comma B for which A is greater than B, then B comma A can't be there, because if A is greater than B, then B can't be greater than A. So that is why it is not symmetric. What about R3? So R3 is symmetric because if I take A is equal to B, so we are containing it is containing only those elements for which A is equal to B or A is equal to minus B. So suppose I take elements 1 comma 1 is there or 1 comma minus 1 is there. Let us understand through example. Because why 1 comma minus 1 is there? Because here 1 is equal to minus of minus 1. And if 1 comma minus 1 is there, then minus 1 comma 1 is also there, because minus 1 is equal to minus 1. Here it is there because 1 is equal to minus of minus 1, right? So it is symmetric here. What about this R4? So R4 is also symmetric because it contains only A is equal to B type element, means 1 comma 1, 2 comma 2, 0 comma 0. So there is no such confusion where that A comma B is in R4 but B comma A is not in R4. There is no such possibility. So that is why R4 is also symmetric. R5 is not symmetric because if A is equal to B comma 1, suppose let us talk about R5. So if I talk about R5, let us take one element. So R5 will have one element, like suppose I take here 3. So it will have 3 comma 2 because 3 is equal to 2 plus 1. So 3 comma 2 belongs to R5. But 2 comma 3 does not belongs to R5 because 2 is not equal to 3 plus 1. Right. So that is why R5 is not symmetric. And what about R6? So R6 is symmetric. Why R6 is symmetric? Use the property that if A plus B is less than or equal to 3, then there is no doubt that B plus A will also be less than or equal to 3. Because if you take any element like A comma B for which A plus B is less than or equal to 3, and we know that addition is a commutative relation, so B plus A will also be less than or equal to 3. So this is also a symmetric relation. So we have seen about reflexive property and symmetric property. Let us consider R1. So R1 has all those elements A comma B for which A is less than or equal to B. So if A comma B belongs to R1, this implies what? This implies A is less than or equal to B. And if B comma A also belongs to R1, then this implies B is less than or equal to A. Both this condition implies that A is equal to B. That is only possible. This is important to understand, that if A is less than or equal to B and B is also less than or equal to A, then it is only possible when both of them are equal. It is not possible in other cases. Like if I take 1 comma 3. So 1 comma 3 is belonging to R1, but 3 comma 1 will not belong to R1, right? So the definition of antisymmetric relation is that if A comma B belongs to a relation R, then B comma A should not belong to R except when A and B are equal. So here we have A and B equal type of elements are there, but otherwise it is antisymmetric, right? So this relation is antisymmetric. What about R2? So R2 is clearly antisymmetric, that when A is greater than B, then A comma B belongs to R2, right? And if A comma B belongs to R2, then B comma A certainly does not belong to R2. Why? Because if A is greater than B, then certainly B is not greater than A. So this is clearly antisymmetric. What about R3? R3 is not antisymmetric because if A comma B is there, then B comma A is also there, except in the case like what I am saying, that here I am writing 1 comma minus 1 because 1 is equal to minus of minus 1. So 1 comma minus 1 is there and minus 1 comma 1 is also there. I hope you got this. This is important. Why 1 comma minus 1 is there? Because 1 is equal to minus of minus 1. This is the second requirement. So that is why 1 comma minus 1 is there. Why minus 1 comma 1 is there? Because minus 1 is equal to B part, that is minus 1, right? But we clearly see that 1 is not equal to minus 1. So that is why it is not antisymmetric. Similarly, R4 is clearly antisymmetric because if A comma B is there, then of course it may be present in the antisymmetric relation because A and B are equal. So R4 is antisymmetric. What is R5? So R5 is also antisymmetric because if A is equal to B plus 1, so whenever A comma B will be in R5, then B comma A can't be in R5. I hope you get it. Why? Because if A is equal to B plus 1, then certainly B can't be equal to A plus 1. So that is why it is antisymmetric. And what about this R6, whether it is antisymmetric? So it is not antisymmetric. Why it is not antisymmetric? Because for example, I take element like 1 comma 2. So 1 comma 2 belongs to R6 because 1 plus 2 is less than or equal to 3. And 2 comma 1 also belongs to R6 because 2 plus 1 is less than or equal to 3. But 1 and 2 are not equal, because if both of them are in this relation, then they should not be equal. But here we note that if both of them are in the relation, means they should be equal. But here we note that 1 and 2 are not equal. So R6 is also not antisymmetric. So R1, R2, R4 and R5 are antisymmetric, but R6 and R3 are not antisymmetric. Now I have to check about transitivity. So here R1 is transitive because if A is less than or equal to B, means if A comma B belongs to R1, it means what? It means that A is less than or equal to B. And if B comma C belongs to R1, this implies what? That B is less than or equal to C. So if I combine both of them, A is less than or equal to B and B is less than or equal to C, then clearly A is less than or equal to C. So R1 is transitive. Similarly, R2 is also transitive because if A is greater than B and B is greater than C, let me write here, if A is greater than B and B is greater than C, then this clearly implies that A is greater than C. So if A comma B is in R3, B comma C is in A comma B is in R2, B comma C is also in R2, then certainly A comma C will be in R2 as well. So here you can similarly check about other relations also. For you, I leave this as an exercise, but before I end it, I want to tell you that here R1, R2, R3 and R4 are transitive.